Hello, I am Patrick Green. I'm a graduate student from the University of Manchester, and today I will be talking about new constraints on heavy neutral leptons from the ArgoNeuT experiment. So heavy neutral leptons are a proposed extension to the standard model that introduces heavy counterparts to the light standard model active neutrinos. These can provide possible explanations for the generation of neutrino mass, for the baryon asymmetry of the universe, and for dark matter. ArgoNeuT was a liquid argon time projection chamber neutrino detector that was located at Fermilab. There's a picture of it on the top right here. ArgoNeuT is this orange structure. The detector was located along the NuMI neutrino beam, approximately 1 kilometre from the target, and collected data between 2009 and 2010. ArgoNeuT's dataset has been used to perform several first neutrino argon cross-section measurements, including the recent first electron neutrino argon cross-section measurement, along with beyond the standard model searches and detector R&D. In this talk, I will present a search for heavy neutral leptons with masses of the order of a few hundred MeV that's recently been performed with the ArgoNeuT detector. So in this analysis, we consider a simple extension to the standard model that introduces a heavy neutral lepton. We assume that it has some mass, and then it mixes with the light neutrinos via some new non-zero mixing angle. We choose to focus on a tau-coupled scenario, in other words, the mixing with the tau flavour is non-zero, and we assume that the mixing with the other flavours is zero. Heavy neutral leptons of this sort can be produced in the NuMI neutrino beam. In the beam, you have 120 GeV protons that collide with a carbon target, and these can produce D and DS mesons. These can then decay to tau particles that subsequently can decay to heavy neutral leptons via some new process, illustrated here. These heavy neutral leptons can be sufficiently long-lived that they can propagate to the ArgoNeuT detector before they decay. And then in ArgoNeuT, we search for the decay signature to a pair of oppositely charged muons. In addition to the production occurring at the target, approximately 10% of the beam protons pass through the target and reach the absorber, where they can produce heavy neutral leptons in a similar way. The absorber-produced heavy neutral leptons, however, are significantly closer to the ArgoNeuT detector, which allows us to probe shorter HNL lifetimes. ArgoNeuT was a liquid argon time projection chamber neutrino detector. There's a diagram of it on the top right here. Its instrumented liquid argon volume was approximately 40 by 50 by 90 centimeters cubed, and its readout consisted of 2 wire planes located at the anode of the detector that collect drifted ionization charge from interacting charged particles. These wire planes had very fine 4 mm wire spacing, enabling high-resolution 3-dimensional event reconstruction. The ArgoNeuT detector was located just upstream of the MINOS-ND detector, which is illustrated on the left here. So this structure is ArgoNeuT, and this is the MINOS detector behind it. MINOS was a magnetized steel and scintillator strip spectrometer, which ArgoNeuT makes use of as a muon back catcher by matching tracks that exit ArgoNeuT with those reconstructed downstream in MINOS. So ArgoNeuT's dataset is relatively old at this point, so you may wonder why would we perform this search for this detector? Well, there's actually several key advantages that ArgoNeuT has that makes it ideal for searching for this particular model and signature. The first is that it's exposed to the relatively high energy 120 GeV NuMI neutrino beam. This allows us to search for heavier heavy neutral leptons than would be possible in lower energy beams, such as that from the SBN programs, only 8 GeV. And this allows us to search these tau-coupled heavy neutral leptons that require this higher energy to produce tau leptons. Secondly, ArgoNeuT was a liquid argon time projection chamber, and this detector technology allows for excellent vertex identification and reconstruction of low-energy particles, which is key for allowing the identification and removal of potential backgrounds. So this is illustrated on the right here. This is showing an event display of an interaction occurring in ArgoNeuT's data. The x-axis shows the wire number, and the y-axis shows the time that the charge arrives on the wire, which gives its position in the drift direction, and the colour is proportional to the charge deposited. So in this event, we can see there are 2 clear, relatively lowly ionizing tracks that could potentially be mistaken for our signature. However, near the vertex, we're able to identify and reconstruct these 2 extra, much more highly ionizing low-energy protons, which allows us to discard this event. Finally, ArgoNeuT was located just upstream of the MINOS-ND detector, which we're able to use as a muon back catcher. This comes with 2 key advantages. The first is that it's magnetized, allowing us to reconstruct the charge of any matched muons, and the second is that its size allows us to distinguish between pions and muons, which is something that would typically be quite difficult to do in a liquid argon TPC by itself. This means that this combination of these two detector technologies is ideal for searching for this mu+, mu- signature with very minimal backgrounds. So in ArgoNeuT we search for these HNL decays to pairs of very forward-going muons. Depending on exactly how forward-going they are, we consider two different scenarios. The first, illustrated on the left, is where the HNL decays to two clearly separated muon tracks, each which can be matched to the MINOS-ND detector. This we'll refer to as a two-track type event. The second, illustrated on the right, is where the pair of muons are so forward-going that they essentially overlap in ArgoNeuT and are reconstructed as only a single track for some or all of the length. However, this single track can still be matched to a pair of tracks in the MINOS-ND detector, which become clearly separated due to being oppositely charged in the magnetic field. This second signature we'll refer to as a double-MIP event, and this signature dominates. We also consider HNL decays that occur in the cavern upstream of ArgoNeuT, where the resulting muons then pass through the ArgoNeuT detector and can be matched to the MINOS-ND detector as before. In this scenario, we consider the region between the end of the Minerva detector, which was under construction during ArgoNeuT's running, and the start of the ArgoNeuT TPC. We also only consider the double-MIP signature, as this is more easily distinguished from background through-going muons. This is an example of what a simulated heavy neutral lepton decay with a two-track signature looks like. So these two images show the two wire plane induction and collection plane views. In both cases, we see that the pair of muons is initially overlapping, however they then become clearly separated into two distinct tracks before exiting the detector. The image on the right shows the ArgoNeuT plus MINOS-ND detector view, and we see these pair of tracks in ArgoNeuT can be matched to a pair of tracks in MINOS, which then curve in opposite directions due to their opposite charges. Looking at an example of a double-MIP type signature, now the pair of muons in ArgoNeuT are almost completely overlapping and are only reconstructed as a single track. However, this track is noticeably more highly ionizing. In the MINOS-ND detector, however, this can still be matched to a pair of tracks, which again clearly separate due to their opposite charges in the magnetic field. So, how do we actually identify whether there is a pair of overlapping muons present? The strongest identifier we have is the amount of energy that the tracks deposit per unit length in the detector, their DEDX. This figure on the right shows the average DEDX over the first 5 centimeters of tracks resulting from simulated heavy neutral lepton decays, and two distinct populations are visible. The first is at around 2 MeV per centimeter, which is consistent with being a minimally ionizing particle in liquid argon. These are events that would be selected as two tracks where the muons are clearly separated. The second, larger peak is at approximately double this, so consistent with there being two overlapping minimally ionizing particles or two muons. We can apply a threshold between these two peaks to distinguish between these two populations. So in the double-MIP case, we require that we have a DDX consistent with being in the second peak, and then we have a single highly forward-going track with respect to the beam direction that exits towards MINOS. For the two-track signature, we require that we have two tracks originating from a common vertex that again are relatively forward-going and both exit towards the MINOS-ND detector. And we require that both of these tracks are consistent with being in this first peak. Once candidate events have been identified in ArgoNeuT, we then perform MINOS-ND detector matching. This is performed by projecting the end of each track in ArgoNeuT to its expected start position in the MINOS-ND detector, and then we compare the position and angular offsets of that to each of the reconstructed MINOS-ND detector tracks to see if they match within some tolerance. So in this example here, these two tracks in ArgoNeuT would be matched to these two tracks in MINOS, whereas this third background muon would be rejected. And similarly, the same procedure is applied in the double-MIP case, but now we're matching a single track in ArgoNeuT to a pair of tracks in the MINOS-ND detector. Once candidate tracks have been identified in MINOS, several additional selection cuts are applied. We require that the two tracks are in time with each other, so they're consistent with coming from a single decay. We require that they're reconstructed as having opposite charges, and that we require that they are consistent with being minimally ionizing particles, muons. Combining all of this, we can look at the overall selection efficiency. So this figure on the right shows the efficiency as a function of the heavy neutral lepton energy for a particular heavy neutral lepton mass, for decays occurring inside the detector in the black, and at two different offsets into the cavern in the blue and the red. For decays inside the detector, the efficiency is relatively high and flat above about 10 GeV. However, there's a sharp decline at lower energies. This sharp decline is a result of one or both of the muons having insufficient energy to propagate to the MINOS-ND detector, and hence we're unable to match them. For the decays inside the cavern, the efficiencies are significantly lower, and this makes sense since in this scenario we're only able to select the most forward-going of the muons, those that remain overlapping by the time they reach ArgoNeuT. Turning to the backgrounds and systematics, the backgrounds to this analysis was simulated using the Gini neutrino event generator, along with a data-driven model of the rate of through-going muons. The dominant source of backgrounds in this analysis originate from poorly reconstructed muon-neutrino interactions that may be incorrectly matched to multiple muons in the MINOS-ND detector. These, however, are typically either topologically distinct or matched to out-of-time tracks in MINOS and hence can be removed. The expected background number of events is tabulated on the right here, and as you can see, the total expected background is very small. This is a very clean signature as a result of the two detector technologies that allow it to remove the vast majority of backgrounds. In terms of systematic uncertainties, these are also tabulated on the right on the lower table, and these are dominated by the large uncertainty in the heavy neutral lepton flux. This arises from the large uncertainties in D and DS meson production in the beam, and also in the uncertainties in the branching ratio of these mesons to tau leptons. Putting everything together and looking at the results, the selection has been applied to the full ArgoNeuT anti-neutrino mode dataset, which consists of 1.25 times 10 to the 20 protons on target from the NuMI beam. In the full dataset, 0 events were observed, which is consistent with our expected background. This allows us to apply a new constraint, which is illustrated on the right here. So this figure shows the region of parameter space that ArgoNeuT can exclude at 90% confidence level in terms of the heavy neutral lepton mass and its mixing with the tau flavor. The existing strongest limits from CHARM and Delphi are also shown. ArgoNeuT is able to set a new strongest exclusion limit for tau-coupled heavy neutral leptons between approximately 280 MeV, where the CHARM limit cuts off, up to around 970 MeV. So to summarise, a search for tau-coupled heavy neutral leptons has been performed at the ArgoNeuT detector. These are produced in the NuMI beam from decays of tau leptons, and we search for the decay signature in ArgoNeuT to a pair of oppositely charged muons. We observe 0 candidate events in ArgoNeuT's data, which allows us to set a new constraint on these tau-coupled heavy neutral leptons with masses between approximately 280 and 970 MeV. In this analysis, we've also developed new techniques to identify these pairs of highly forward-going muons originating from this type of decay. And these will be applicable to future searches in other liquid argon TPC detectors, such as the upcoming June NEAR detector, which is expected to be very sensitive to this model. A paper describing this analysis has now been accepted by PRL and is available on the archive from here. Thank you for listening. I'll happily answer any questions that you may have in the upcoming discussion session.